Hello everyone and welcome to part 2 of the linear regression implementation with Python. This will be the final video for the linear regression section of this course, so let's finish strong. In the last video we went over some basic EDA and visualizations, how to train and fit your model to your data, and evaluating the model. So in this video we're now going to shift our focus on how to get predictions from our model. So let's get started. The first thing we're going to do is to grab predictions from our test feature set, and so we'll need x_test to do this. To clarify and review from last time, x_train was used to train and fit our model to our features, and x_test will be used as the test set for our model. With x_test, we're essentially going to be passing in feature data that the model has never seen before, and we're asking the model to make predictions based on these features. And remember that x_test only contains the feature columns. We can obtain our model's predictions by passing in predictions equals lm.predict x_test. So this will help us grab the predictions from our test set. Let's run that. Great. So now that that's run, let's see what our predictions look like by passing it in as just predictions. We can just run like this. And as we can see, this is an array full of all the house price predictions that are made by our model. These numbers are the predicted prices of the houses based on the test set features. So there you go. These are all house prices. So now that we have these predictions, right, we also know our actual correct prices of the houses, and that's going to be in our y_test set, which contains the target data column. And we can see that by saying y_test. And if you remember from the lecture videos, there are actual and predicted values. And in this case, these house prices in y_test, in this and numpy array here, these house prices in y_test are the actual prices, and the predictions array contains our predicted values, as I showed in the previous cell. So now that we know this, what we want to do is we want to see how far off our predictions are from these actual house prices. And so basically we want to investigate the error or our residual values. So as a quick visual analysis of our residuals, we can use the matplotlib scatterplot. And as a quick review of what a scatterplot is, scatterplot graphs basically they graph pairs of numerical data with one variable on each axis. And in order to look for a relationship between these, and what they're basically doing is they're looking for a relationship between these variables on each axis. And if the variables are correlated, the points will fall along an imaginary line, and the better the correlation, the tighter these points will hug this line. So in our case, we'll be passing in y_test and predictions to compare the predicted house prices and the actual house prices. So if our scatterplot lines up fairly straight, that means our model did a fairly good job. But of course, if your scatterplot is producing a perfect line, that means your predictions perfectly match your actual values, which is extremely rare. So a little bit off isn't too bad. Let's create the plot by saying, by passing in plt.scatter y_test, predictions. So basically, we're taking in both of these set of values to create the scatterplot. And as you can see in our case, we can see that for the most part, the model did a fairly well job with the more common average house prices compared to the and this is because in these house prices, this imaginary line seems to be more tighter there. As you can see, the more tight and clustered here, so that means our model is doing pretty well with correlating the actual and predicted values. However, we can also see that the model seems to have a little more trouble with predictions for house prices with much higher values in the 40,000 to 50,000 range. So now that we made our scatterplot, let's look at one more visualization, and this will be a histogram for the distribution of the residuals. And we can do this by saying sns.displot, and then we'll pass in the difference between our y_test and our predictions. And remember that this difference between the actual values, which is our y_test, and the predicted values, which is our predictions array, is called the residuals. And spell that right. There you go. So if we run this line of code, There you go. So now we can see a histogram of all of our residuals. And from this histogram, what we're trying to see is the distribution. Is it a normal distribution? And in our case, it's somewhat normally distributed. So our model didn't perform too bad with these predictions. But what this is telling us is since that it wasn't like normally distributed properly, this means that maybe a different regression model may be better suited for our data set. But if you do have a normal distribution in your residuals, that means that your model is fitting well with your data, and the linear regression model would be really good for it. But as you can see, the residuals still seem to be fairly distributed properly, so the model is doing a fairly good job with its predictions. So now we're going to move on to our final topic, which is going to be regression evaluation metrics. So let's first start off with the import for this, which will be from sklearn import metrics. All right, so before we actually move on with the code, let's give a brief summary about what I'll give a brief summary about what regression evaluation metrics are. So to quickly sum it up, regression evaluation metrics are just variations of the difference between the actual true values and the predicted values. So basically, they're just manipulations of our residuals or our errors, or basically the manipulations of this difference between the predicted and the actual values. And the three most common evaluation metrics for regression problems are mean absolute error, or MAE, and that's going to be the mean of the absolute error of the error residual. The next one is called mean squared error, which is the mean of the squared error, and then root mean squared error, which is just the square root of the MSE. So let's first get started with MAE. MAE is basically just the average error, and we can obtain it by passing in our y_test and predictions array into the mean absolute error function from scikit-learn. Let's do this by saying metrics.mean_absolute_error, and then we'll pass in y_test comma predictions. And if we run this, we can we'll obtain our mean. Yeah, there you go. So this is going to be our mean absolute error for our model. MSE, on the other hand, is more popular than MAE because MSE punishes larger errors, and this is because it takes larger errors into more of an account because it's actually squaring the errors when producing the value. So this is actually more applicable and useful for real-world applications where we want to prevent large errors as much as possible. So we can obtain this MSE value similarly to the MAE by passing in metrics.mean_squared_error. And then like how we did for the MAE, we'll just put in our parameters as y_test, y_test, and the predictions. There you go. And that's going to be our mean squared error for our machine learning model. And finally, I'm going to go over RMSE. So RMSE is also really popular to MSE. It's really similar, but the only difference is that, like I said, you're taking the square root of the mean squared error. And it's really popular because you can directly interpret it with your target variable values. So we can obtain the RMSE by passing in NP. So it's a little bit different. You're going to have to use the np.square_root function since we're taking the square root of this value. So we're going to say np.square_root, and then we're just going to input the mean squared error the mean squared error value like this, and then if we just run that, great. So that is the RMSE value for our linear regression model. Ultimately, all these regression evaluation metrics are just they're all loss functions because we want to minimize them as much as possible in order to optimize our model's performance. And like I said, loss, residual error, those are all synonymous terms. And that is the end of this video. Congratulations on your first real-world implementation of linear regression. I hope you're able to learn and get a lot out of these lectures, and I wish you the best of luck in your machine learning journey.